right. So chapter 26, it's been a while, right?
Yeah, it's been a while.
Mm, all right, so this chapter is about ends and coends, and it starts by reminding us about um, the home functor and about profunctors. And there's this, I think this first paragraph here is actually pretty interesting. There are many intuitions we may attach to morphisms in a category, but we can all agree that if there is a morphism from the object A to the object B, then the two objects are in some way related. And a morphism is in a sense a proof of this relation, and is clearly visible in any poset category, where a morphism is a relation, right? Specifically, it's the less than or equal to relation, right?
Yes.
Usually. And then it says there may be many proofs of the same relation between two objects. Those proofs form a set, which we call the home set. We saw this before, right? Way back at the beginning of the book.
Yeah, which is basically the category symbol. So C and in parentheses in the two objects separated by comma. That's the notation of the home set.
Yeah, and it actually denotes the set of morphisms between the two objects, rather than anything within the category itself necessarily.
Yeah.
When we vary the objects, we get a mapping from pairs of objects to sets of proofs, and this goes back to the notion of a morphism being a relation, a proof of this relation, right?
Yes.
And this mapping is functorial. It's contravariant in the first argument and covariant in the second. Um, we can look at it as establishing a global relationship between objects in the category, and it's described by the home functor.
And this
This.
is a home functor because we are going to the set category, right?
Yes, exactly.
Yeah, I need to keep reminding myself what the heck is a home functor again? And then, oh, it's the functor that goes into to set, which then begs the question, why the heck we don't we call this the set functor?
That's an excellent question, actually.
I think it's because of
Something.
homomorphisms or whatever you say it. I think that's the reason, but I can't recall at the moment.
Well, anyways, and if you remember these dashes and this double dash, which looks like an equal sign, those are actually like um, they are like type parameters or something.
Yeah,
Like
they are type
I,
holes, right? That you're gonna fulfill.
yeah, and I don't really like this notation, but it is what it is.
I also don't like the notation.
In general, any functor like this may be interpreted as establishing a relation between objects in a category. This goes back to the first paragraph. A relation may also involve two different categories C and D, and a functor which describes such a relation has the following signature and is called a profunctor.
Yeah, which is kind of interesting because you're grabbing the opposite category of D, right?
Yeah,
Yeah, so we are grabbing the opposite.
and mathematicians, I actually found this kind of funny when I saw this the first time. They say it's a functor from C to D. Notice the inversion. Like, no risk of confusion whatsoever, right?
No risk of confusion. But can you go back a little bit? Can you scroll up?
Screw up.
I forgot to ask the question. Why are we going from a pair to a set in which the first member of the pair is coming from the opposite category of C?
Because this is contravariant on the first hole here. That's why this is the opposite category and rather than C, right?
Yeah, but this is establishing a functor talking about the home sets, right?
Yes.
But so the tuple is basically the members of the set, the members of
Yeah,
the
this is
category, I guess.
this is mapping the like if you have a home set, this is mapping the two objects in the source category, or well, technically one of them is in the opposite of the source.
Yeah, but why?
Two
That's what I don't
they are
understand.
map and this goes to sets because it's mapping those two objects to the home set itself. You see?
No, 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 no. Everything after the arrow I understand. What I don't understand is why we are grabbing the objects from the category from the instead of CC we have COPC.
if we had CC, it would not be contravariant in the first position
It
because
wouldn't, but my question is why do we want it to be contravariant?
uh, I think that may have something to do with the composition rules for arrows
Mm.
because yeah, because this first C is at the beginning of the arrow, right, at the starting point, and the second C is at the end of the arrow.
I think maybe it's also related to the fact that we want to leverage profunctors and we need a contravariant component. Maybe all of these would not be possible. The entire idea of the end of the coend would not be possible without the profunctors. Hence, we need to have the contravariant somewhere. And then we decided to go with this. But I think this and what you said are related, right? Because the composition of arrows and the profunctors, well, that's
Yeah,
basically the same thing.
yeah.
Okay, that's enough of an answer for me.
All
That's the
right,
first of
moving
my
on.
many questions, but we're gonna go over.
Yeah, mathematicians say it's a profunctor from C to D. Again, no risk of confusion, right? And they use this slashed arrow symbol, which is like, okay, I guess.
I think
Not sure
they do
why.
it like this because it's consistent with the other brothers. Like all the other functors make sense to talk in this notation, and instead of creating an isolated case, they decided to keep it. And
But
well,
why flip the letters?
they no, we are flipping the letters. We are going from D to C, right? All the other functors they go from the first category to the second. The profunctor is the only one in which we reverse them.
No, we're still going from one category to the other. It's just that this is like if you try to treat this as a functor, um, like this is actually contravariant on this parameter, which we usually think of as the source, right? The starting point of the well, I can't really say morphism because we're talking about functors here, right?
No, I think I don't understand what you're saying. The guy on the left is supposed to be the beginning, which makes sense, like notationally. But I think when we saw profunctors all the way up there, we would call the profunctor CD, right? Which is from D to C instead. So again, whatever. It's a no risk of confusion.
No risk of confusion. That really has become a meme, hasn't it?
Well, it is
Um,
what it is.
okay, you may think of a profunctor as a proof-relevant relation between objects of C and objects of D. Yeah, this follows, where the element of the set symbolize the proofs of the relation. That's kind of profound. And whenever this is empty, there's no relation between A and B, and they don't have to be symmetric. So another useful intuition is the generalization of the idea that an endofunctor is a container. Um, and a profunctor of this type it can be considered a container of B's that is keyed by A's. Um,
Yes.
and in particular, an element of the home profunctor is a function from A to B. So there you go. Intuition from knowledge about functions is allowed here. Um, and then we get into Haskell. So a profunctor is defined as a two-argument type constructor P with this die-map method, which lifts a pair of functions and one of them is backwards.
Yeah, and
Again,
then
because
again, uh, this is hella confusing if you're not used to it, but if you play around with it, it will make sense. And there's also other intuitions that you can leverage, like what you, well, Marinho told me one before the recording anyway.
I think it's worth mentioning here. Basically, you can think of this as okay, there's a hole which is A-shaped, and if you put an A in that hole, a B comes out the other end. That's straight up function-based intuition, right?
Yes.
But if you want to compose something with this hole, with this A-shaped hole, you need to you need to somehow provide an A to it. And if you look at this function here, you can interpret it as saying, okay, I can have this C-shaped hole. If you put a C in it, an A comes out the other end, right? So you can plug this A object that comes out of this into this hole here, like a pipeline.
Yeah, I think to enhance your analogy, I would suggest to think of the P's as arrows as well.
Yeah, that's actually what I do normally when thinking about uh, this kind of,
Yeah,
well,
contravariance in general, I
profunctor.
guess.
Yeah, contravariance in general. It's easier to think about this as if it's an arrow, and then it starts
Yeah.
making a bit more sense.
Yeah, because if it's an arrow, you already have on hand a function from A to B, right? And you
Yeah,
want to culminate into a function from C to D. Then it makes perfect sense because then you can grab the C, which is the first argument, the argument of the first parameter on the left. And you're gonna get an A out of that. You already have a function that picks an A and gets you a B, so grab the B out of that. But conveniently, you also have a function that picks a B and returns a D.
and there you
So
go.
exactly. So maybe that's the secret of thinking about holes and swapping the P's with arrows. Basically, that's the secret sauce.
Yeah, this is a very, very handy intuition, I would say. The functoriality of the first functor tells us if we have a proof that A is related to B, then we get the proof that C is related to D as long as, you have these other proofs as well. Well, not proofs in this case, morphisms, right?
Yes.
Or you can think of the first function as translating new keys to the old keys, right, from C to A. And the second function modifying the contents of the container, so this B becomes a D instead. So, yeah. For
Yeah, but that
perfunctors,
I don't like that analogy though. That analogy of mappings because that puts us back into having containers. And then if you interpret P as containers, you get back to the original problem.
yeah, I don't like that analogy either. I prefer to think about them as arrows, actually.
Yeah, well, but you can think of a function as a map, right? Like the map data structure. Like if you force a little bit, what is a map? It's a set of functions.
Well, it's a function where the input type is the type of the key, and the output type is, well, the output type, I guess.
Yeah. So if you can understand a function as a map in that case, like a map like with capital M, like a data structure.
Like a
Yeah,
dictionary.
exactly.
Uh, and here's the part that is relevant to this chapter. For profunctors acting in one category, we can extract quite a lot of information from diagonal elements of this type from P from A to A. And we can prove that B is related to C as long as we have this pair of morphisms. This is basically just, B to A to C. And even better, we can use a single morphism to reach off diagonal values.
Yeah,
And this is
diagonal
like,
values. Okay, so that's the thing. That goes back all the way to the definition of profunctors, and there's a diagram there showing how the profunctor works. And there is a diagonal in there. So I think
uh,
that diagonal is this diagonal here.
I can show the diagram if you have the page number easy.
I may have the page number easy. Wait a moment. Okay, I do
Uh,
have it. It's in page 80, 89 of the PD of the book and 160, 104 of the PDF.
104.
Scroll down.
Is this the page? Yeah, this is almost there. Functors. 89 of the PDF, right?
No, yeah, 89 of the book.
89 of the book.
No, no, 90 of the book. Sorry.
Oh, 90.
Yeah, I think we are using different versions of the
Yeah,
PDF.
yeah, I think we are actually. What's the chapter number?
No, that's it's 80.8.7. 8.7. That's what we want.
Oh, it's the next chapter.
We are definitely
Uh,
using different versions. I don't have almost 500 pages on my version.
8.7, 8.3, 4, 7. There we go.
What the heck?
Here.
Okay, so no, but wait, but something happened to your screen.
What do you mean?
I would stop sharing the screen, sharing again. There are a bunch of artifacts. There's something flickering on the screen right now. No idea what happened
Okay.
there. Oh, definitely.
Is this better?
Yeah, this is definitely working. Okay, so there it is. I think that diagonal that we are talking about is that one.
It's not really.
So then I don't think it makes sense.
No, what it means by diagonal is okay, what happens if you have a sequence like and you have a table where the sequence is like the labels on both axes of the tables, like both the rows and the columns. What happens to if you look at the diagonal of that table?
I don't understand that at all. Can we go back to where we were? I think it was page 404 of the PDF.
Yeah, here.
Yeah, so we can use a single morphisms to reach off diagonal values. For instance, if you have a morphism, this, we can lift a pair that go from PBB to PAB, and that is
Yeah,
not a
because
diagonal that we saw there.
by diagonal here it means both sides of the pair are the same.
Both
Like,
sides of the pair are the same, but they aren't, right?
well, PAB isn't, but PBB is because B is equal to B.
Oh, okay, so we're talking about that diagonal. I didn't understand that at all.
Yeah,
Okay.
it's saying we can use a morphism to reach off diagonal values. So if we have, okay, diagonal elements of the type PAA, right? A equals to A, this is in the diagonal. If you make a table with like all the possible, like if you make a table listing the possible values from the left as the columns and the right as the rows, the diagonal is the place where the value is the same on both sides, right?
Yeah.
That's what it means by diagonal. Diagonal elements in particular.
So off diagonal values means the ones in which we have the two same thingies.
They're they're different if they are off the diagonal.
Oh, that makes sense actually. Okay. Okay. Actually, I got it.
All right, and um, yeah, and basically you can use a single morphism to reach out of the diagonal because this is basically exploiting the fact that this is contravariant on this side and it's covariant on this one. So actually, uh, you can kind of cheat by flipping the direction of the arrow by applying it to the different places of the profunctor, you see?
Yeah, that's kind of crazy, huh? Because if it's on the first position, it's contravariant, right?
Yeah,
And if it's on the second position, it's covariant.
yep.
So if I have a function going from B to B, and I want to have a function going from A to B, yeah, that this makes perfect sense actually. Okay, okay. The analogy with the functions really helps me. Holy jeez. Okay.
Functions are life, man.
Functions. Okay, let's continue.
Dinatural transformations. Strange word. They make sense, so it gets a pass. Um, since profunctors are functors, we can define natural transformations between them in the standard way. In many cases, though, it's enough to define a mapping between diagonal elements of two profunctors. That's what we're getting at here. Such a transformation is called a dinatural transformation, provided it satisfies the commuting conditions, which you're going to see soon. Um, that reflect the two ways we can connect the diagonal elements to the non-diagonal ones. And the natural transformation is a family of morphisms like this. Uh, alpha at point A is an arrow from PAA to QAA.
So keeping that analogy, we are basically mapping functions.
Basically, yeah,
Damn.
basically.
Actually, if you really think about it, contravariant and profunctors are really about manipulating functions.
Yeah, they kinda are.
Like they are the pinnacle of high order functions.
basically.
Okay.
Um, and here's the diagram that needs to commute for this to be a dinatural transformation. So if you start from PBA, then there are two ways you can get to a diagonal element, right? By mapping
Yes.
F from A to B uh, covariantly on the right or contravariantly on the left. Then you apply
Yes.
alpha at the different points to go from P to Q, and then you lift the F again using the Q to go to QAB.
Yes. Yeah, this makes way more sense after the analogy, man. Damn.
Yeah. Notice that this is strictly weaker than the naturality condition. If A were a natural transformation um, in this category, the above diagram could be constructed from two naturality squares and one functoriality condition, which is basically the same thing, but there are these extra arrows in the middle. And the alphas, as you can see, they are keyed by both.
Yeah, we never seen this before, right? I think in natural transformations it was only one letter keying the thing. Now we have two letters.
Yeah, that's because um, this is a
Oh, that's
functor
because
with.
the functor requires it has two facets, I guess.
Yeah, this is a functor with two parameters. So a natural transformation would be keyed by both of them,
Yeah, that
right?
makes sense. Actually, that makes sense.
And that gives us the ability to do this, right? There's this additional arrow here in the
Yeah,
middle that is not in the diagram on the top.
yeah.
Um, and this is assuming the profunctor Q preserves composition because, well, there's an identity being used here, right? And it needs to compose uh, with the Fs, basically. I started thinking about this just before the recording. What about the arrow from QBA to QAB using two Fs? It's not in the diagram, but I think it should be.
Oh, do you mean applying F both covariantly and contravariantly?
At the same time, yes, because if Q preserves
Hmm.
composition, then composing this ID of A with this F is the same as just F, right?
And the same applies on the other side, right?
Yeah, yeah. So why
Okay.
not show the extra arrow here as well? Like,
That's a very interesting question, actually. That's actually. I wonder if there's a type problem. Oh yeah, I think we're gonna have a type problem because uh, if you like the F is being used, it has a specific type signature, right? If we use it
it's
contravariantly, I think at least GHC will. I don't think that would work with GHC because the types would not match. You're gonna have like little a's and little b's mismatching on the other case. Like I don't know if I'm making my. There is a blog post about this. There is a blog post, a Haskell blog post about this,
of course
explaining
there is.
explaining why. Like because at first glance, it should like it makes sense to assume that a contravariant is just as normal as a functor. But then the post makes very explicit that the little letters, the A's and the B's will be misaligned, and then the compiler will not be able to do the thing. So maybe that's the reason that they are not showing it in here. Maybe there are more complications, but that's an interesting idea to say the least.
I'll have to try it out in the JHCI later
Well,
because this
definitely,
is
definitely.
yeah this is kind of bugging me. This missing arrow here.
I think you're gonna have a type problem. Let me know what happens when you do.
I will. Notice that a component of a natural transformation alpha in this category here is indexed by a pair of objects. Yeah, right, because it's not dinatural, it's just natural. So because there's two
That's kind of
parameters,
funny.
the functor. Yeah, yeah, it
That's
kind of is.
okay.
Yeah, and in contrast, a dinatural transformation is indexed by one object because it only maps the diagonal elements of the profunctors.
Yeah, yeah, yeah. That makes sense with what you explained of diagonal. Okay, let's finally go to ends.
And we are now ready to advance from algebra to what could be considered the calculus of category theory. and this is a weird analogy, but okay. The calculus of ends and coends borrows ideas and even some notation from traditional calculus. Um, and in particular, the coends may be understood as an infinite sum or an integral, whereas the end is similar to an infinite product. I don't think these are actually that common in calculus, are they?
Uh, yes, it's called a product progression. Ah, damn. Okay, but it's do do you know the sequences? Like we have a bunch of well, I'm not let's not dive into if that's real or not. I'm just giving you an example. If you have like half plus 1/4 plus 1/8 and so on and so forth.
But that's just an infinite sum, no?
Yes, yes, but you can do the same swapping the sums with the product. And there is
I
algebra related to that stuff.
I see.
And I don't know
That's
the direct delta function, by the way.
yeah. An end is a generalization of a limit, which is saw way back, like chapter what 6 or 7 or something,
Yeah, that's very old. Limits and colimits, that's very freaking old.
with the functor replaced by a profunctor. So instead of a cone, we have a wedge. Um, Base is formed by diagonal elements of the profunctor P, and the apex is an object. Here a set because we are considering set-valued profunctors. And the sides are a family of functions mapping the apex to sets. And you can think about it as a polymorphic function with this type, which is a very weird type if you think about it.
Yeah,
Because like it's introducing this A here out of nowhere.
yeah. No, 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 you're not
Unlike
introducing out of nowhere. The quantifier is introducing it.
no, no, there
The
is a for all. That's fine. The thing is, there's no way in this apex, right? But we're saying that for all possible ways, we can go from the apex to a profunctor with that A as
Yeah,
a
but that's the same
parameter.
idea of limits and colimits, right? Like, as far as I remember, the idea was instead of having a wedge, you have a cone, and in one of them you are converging everyone to the single thing, and the other one you are diverging everyone, uh, generating everyone from one single thing.
Yeah.
Yeah, so this is the
Um,
same
un-
idea.
yeah, same idea. Unlike in cones, within a wedge, we don't have any functions that would connect the vertices of the base. However, as we've seen earlier, blah blah blah, with any morphism, we can connect both PAA and PBB to this set here. Yeah, we just saw that. And therefore, we insist that this diagram commutes. So if you go from the apex to PAA and go to PAB, that should be the same as going to PBB first and then lifting F on the left to go
Yeah,
to
and this is the
PAB.
wedge condition.
Wedge condition. And it can be written like this, or using Haskell notation.
Yeah, makes sense.
We can now proceed with the universal construction. Um, Again, we saw this a lot of times already. To define the end of P as the universal wedge, which is the set E and a family of functions pi, and I'm not sure why pi, but whatever, such that for any other wedge with the same apex, well, with an apex A and a family alpha, there's this unique morphism here. Yeah, we saw this before, like, I don't need to belabor this, right?
Yeah, I think like, and let's actually recap a little bit. So, universal construction is the act of enumeration, right? You're enumerating the cases and then filtering out the ones that follow the property. That's what I remember
Yeah,
for universal construction.
yeah, and
Then,
you're basically using this age here needs to be unique for any particular pair of A and E.
yes. So you have a set E, a set of what? Let's just start with that question.
Well, in this case, it can be anything, right? Because the apex is not even, it's just an arbitrary type.
Okay. So you have a set of something, and you also have a family of functions pi, okay, such that from any other wedge with the apex A and a family alpha, there is a unique function that makes all triangles commute. I don't know if I completely understand what that means, but let's go. Let's continue.
The symbol for the end is the integral sign with the integration variable in subscript, and I have a slight issue with this because this is literally, if you scroll down a little bit, this is literally just a for all. So like, whatever. But this is notation, so
Components
no
of
risk to
pi are
confuse.
called projection maps for the end.
Yeah. So basically, um, the type signature of this pi function would be for all c takes a PCC, and this is in parentheses, and it returns a PAA, and there's a for all around the entire thing as well because of this.
Okay, that makes sense. Now I understand why I was confused. Okay.
Note that if C is a discrete category with no morphisms other than the identities, the end is just a global product of all the diagonal entries of P across the whole category C. And later, I will show you that in the more general case, there's a relationship between the end and this product through an equalizer. We saw this when we are looking at limits as well, right?
I don't recall. I think it was delta C, the equalizer name,
Yeah.
but I have very little
Uh,
recollection of that.
in Haskell, the end formula, this one, translates directly to the universal quantifier, which is why they actually didn't need to borrow notation from calculus. They could just have used the turn A as
Yeah, no,
usual,
but I
but
think it came, like I told you, I think it came, the sequence of acts was they made a parallel and then the notation came. Because we cannot understand the parallel, we cannot justify the notation. So let's just call it for all from now on.
okay. Strictly speaking, this is just a product of all the diagonal elements of P, but the wedge condition is satisfied automatically because of parametricity. This is being milked a lot since the beginning of the book. Like
What do you mean?
this, like every time, like parametricity makes things. I'm not sure if you know this, but like a lot of conditions that you would have to establish are satisfied automatically. Like it's just crazy.
Did he bookmark, well, add that footnote more than once? I don't remember.
And no, this footnote is specifically for this blog post, pro-functor parametricity, not. But like parametricity in general has been mentioned a lot of times already.
What are we calling parametricity in this case?
Uh, Basically, if you have a parametric polymorphism here, like this
Yes.
A-type variable, you're not allowed to actually, peek inside of the implementation of the in the details of this A. Like you can't, you have to treat it as a black box necessarily.
Oh,
Like that's
okay. Okay, but that is being milked because, well, because that allows us to do very fancy shit.
yeah, they call it theorems from for free
Yeah.
somewhere. I
Yeah,
don't.
no, Bartholds also calls this.
Yeah. Um, Anyways, for any function f from HB, the wedge condition reads this, or with type annotations, right? The
Yes.
subscripts here. And both sides have this type, which is a very unusual type, but okay.
Yes.
And pi is the polymorphic projection with this monstrosity of a signature, and in the end, it's just the identity function.
This monstrosity, that's good.
Yeah, and here's the nested for all on the left of the arrow, as we mentioned before.
Yeah, it's a for all on top of a for all. Damn.
Yeah, this is like nested for alls
For days. Yeah.
for days. Here, the type inference automatically picks the right component of E, which is like, okay. Just as we were able to express the whole set of commutation conditions for a cone as one natural transformation, we can do the same thing with a dinatural transformation for the wedge conditions. Um, for that, we need a generalization of the constant functor, delta C, which we saw before, right? To a constant profunctor that maps all pairs of objects to the single object C, and all pairs of morphisms to the identity for this object, which is kind of crazy if you think about it.
Yeah.
And then the wedge is a dinatural transformation from that functor to the profunctor P. And the dinaturality hexagon uh, shrinks to the wedge diamond. So the two diagrams that we saw earlier, basically.
That sentence is crazy.
It
Okay.
is. Yeah, like there's a lot of interesting linguistics going on here, even though this book is not about linguistics, but whatever. But yeah, that hexagon diagram becomes the wedge uh, diagram when we realize that this constant delta c lifts all the morphisms to the identity function. Yeah, it's like,
Damn.
yeah,
Yeah,
no.
but again,
When I
like, okay, go on.
Yeah, no, when I saw this, I was like, okay, we did all of this, and in the end, it's like an identity, and it's like,
No, but that's a very powerful example for everyone that is learning any functional language. Why do we care about the identity? People ask this constantly. Why do we
why do you
need
care
such a
about
function?
why do you care about the number zero? You may as well ask that, right?
Yeah, I would say so.
Um, Ends can also be defined for target categories other than set, but here we are only considering set-valued profunctors and
Okay,
their
so
ends.
aside the memes aside, what we just established is that uh, we are basically making a convergence process, and we are calling that the wedge.
Yeah.
Okay.
Ends as equalizers. The commutation condition in the definition of the end can be written like this. We saw this kind of thing before, right?
Yeah, we saw
Uh,
this kind of thing before. Yes.
um, let's define the two functions using Haskell notation because mathematical notation is less user-friendly in this case. I agree with that, actually. Um, so lambda and rho, which are the two versions of DIMAP with the f on the left and on the right, right?
Mhm.
They map diagonal elements to polymorphic functions of this type, and here's the type alias, which, yeah, this eliminates these a and b variables from having to be in the signature. They make everything look nicer, right?
Mhm.
When we get here. These functions have different types, but we can unify them if we form a big product using this. Um,
These are the
diaport of,
diagonal elements, right?
yeah, diaport of P is for all A, PAA, so diagonal elements.
Yeah.
And then the two functions, lambda and rho, that we saw before, they induce these mappings from this product to um, this,
Wait a moment. We are
basically.
going from mappings of the diagonal to mappings of outside of the diagonal.
Prod P, yeah, we are.
Can you go scroll up? Let me see again lambda p.
Lambda, okay.
Yeah, so you receive a PAA, which is diagonal. You receive a function that
From A
maps
to
A's
B,
to B's,
and
and
you
you're
go
gonna
out
read.
of the diagonal.
Actually, that makes sense. You're going. Only one of them is getting out of the diagonal, I guess.
Yes, only one of them.
Okay, no,
And
that
row is
actually
the
makes
same
sense.
thing, but on yeah, row is the same thing, but it's on the other side,
Yeah, no,
basically.
this
You know.
actually makes sense. It's kind of surprising how much more I understand after I get a good enough analogy. Because before I was completely lost, and I read this twice, but now it makes
Well,
sense.
I'm glad to help Lemus.
I appreciate that.
All right, so lambda p and row p, which
Oh,
using
yeah,
the
yeah, no,
new
this makes
fancy
perfect sense
types.
now.
And then the end of p is the equalizer of these two functions. These two functions. Um, Remember that the equalizer picks the largest subset on which the two functions are equal. In this case, it picks the subsets of the products of all diagonal elements for which the diagrams commute. So
Okay, I need to
yeah,
remember what is an equalizer again?
an equalizer is
Is it a set in which makes the two ends of equal?
it's yeah, like it's a mapping that restricts the domains in such a way that they are equal within that limited domain, essentially.
Okay.
Natural transformations as ends. The most important example is the set of an end is the set of natural transformations. This is a recap, basically, right? Family of morphisms picked from home sets of this form, right? Because natural transformations go from like right functor and a type parameter to another functor with the same type parameter, and this is just a home set of that.
Yeah.
Um, if it weren't for the naturality condition, they would just be the product of all of those home sets, but in Haskell it is because of parametricity strikes again. I told you, man, parametricity. It's everywhere in category theory.
Well, it's kind of useful, not gonna lie.
Outside of Haskell, though, not all diagonal sections across the home sets will yield natural transformations, but notice that this mapping um, from A to B, from a natural transformation of A to B to the home set is a profunctor. So it makes sense to study its end, and this is the wedge condition. So we just saw this before, we just instantiate some variables, right?
Yeah.
Let's pick one element from the set. The two projections will map these elements to components of a particular natural transformation, and we call them tau A and tau B.
Wait a moment. What? Let's go back. We are grabbing an element from that set. That set is the set is a home set, right?
Yeah,
For all in that home set, going from FC to GC.
for
That's
all
the
C, yeah. Yeah, you
for,
can read this integration with the C on the bottom as a for all C, basically.
so for all C,
Yeah.
see the category.
No, for all little c,
Oh,
the
little
variable,
c. Okay, for all little c, we have a home set in which we have morphisms going from FC to GC.
yeah.
And what is tau doing in regards to this?
Uh, we're picking an element from this set, and tau are the
Taus are elements of this set.
tau are elements of this natural transformation. Yeah.
Okay, okay, I got it. Thank you.
Okay, we're picking an element from this, so we're picking a natural transformation, and then the two projections, these two, right?
Mm-hmm,
This,
mm-hmm.
they will map that element to the component to two components of this, yeah. In the left, we lift the identity and g of f using the home functor, and this is implemented as a simultaneous pre and post composition. We saw this before,
We also saw
a
this
couple
before.
times, a couple times actually, right?
I don't remember about the couple times, but at least one chapter.
When acting on tau at A, the lifted pair gives us this,
Okay, so
and
let's
the
let me
other,
try to understand what the heck is going on there. Why are we
okay,
grabbing? We are grabbing ID at A and GF because that's coming from the pair that he's listing there.
it's this one.
It's one pair available in that home set.
Yeah,
Okay. So then we are putting the tau in the middle. Why are we doing that?
because this is just this thing applied, this arrow here applied to tau at A.
That thing, but that thing is a home set. What do you mean?
No, not the thing, the home set, the thing, this particular lifting here. Like if you lift this pair of functors in, fmap it or whatever.
Yeah.
Actually, this would be a die map, right?
Yes. Die map. I think in Haskell we're gonna see later this is a die map.
Yeah, a die map on arrows is a composition on both ends, basically.
Oh, that
That,
okay. That's what the piece that I was missing. That's right.
Yeah, so acting on tau at A, it gives us this, and the other branch of the diagram, which is this one, right,
Yes.
with the f of f on the left, gives us this, and the equality of these two things, which is what the wedge condition demands, is just actually the naturality condition, which we
Crazy.
get because we are assuming this is a natural transformation to start with, right?
That's crazy.
It is. And now we have the pun, of course. Yeah. So the dual to an end is called a coend, and it's constructed from the dual to a wedge, which is called a co-wedge, not a cow-edge. Yeah.
Yeah.
The symbol, they chose the integral sign, but with the variable on the top, which I think is no risk of confusion, but whatever. Just like the end is related to a product, the co-end is related to a co-product or a sum, and in this respect, it resembles an integral, which is a limit of a sum, which is,
Red,
this
red,
is
red.
a,
Go on.
yeah, this is a bit more understandable, but I still don't like it anyways.
No, of course. I'm not surprised.
Um, Rather than having projections, we have injections. That's normal, right? We saw that before. Going from the diagonal elements down to the coend, and if it were not for the conditions for the co-edge, we would say that it's either a PAA or PBB or PCC and so on. Or we could say that there exists an A for which the co-end is just this. Um, and in pseudo Haskell, because it's not real Haskell, Haskell doesn't have an exist, but it would be this.
Yes.
If it and there's actually a way to encode exists in Haskell, like there's which is like this, which is like I'm kind of sad that you have to do this, but it is what it is, I guess.
Yeah, but that's kind of. I'm a little bit confused by this trick because it's different to say exists an A such as there is a PAA, saying for all A, co-and PAA. How are these two equivalent?
It's because this coend, this constructor here, it is semantically a function, right?
Yes.
And if you scroll down a little bit, there's, well, we can pick it up here, but like there's this basic equivalence here that we'll get to in a minute that says a function taking an exists is actually equivalent to a polymorphic function, which is like that's why the for all is used for.
No, I also didn't understand this trick either. That's why I'm asking it with the previous one to see when this comes along, I can understand it. I don't see where are these two things are equivalent. Even assuming the definition of equivalence that we are going to be using.
Yeah, Haskell syntax
What is
is.
this? But what is the intuition that you use to explain to yourself this translation?
The intuition actually is from. Okay, do you know how much do you know about classical logic?
About what classical logic?
Yeah, classical logic,
I,
specifically Aristotelian logic.
I know a little bit.
All right, so if you know classical logic, you should at least be aware that there's a relationship
Hmm.
between for all and exists.
Yeah,
Okay?
that very understandable.
Yeah, and the relation is that uh, for all a x of a, whatever x is, um, if you basically say every a is a p for some property p, right?
Wait,
That's the same as saying,
you cut it a little
okay,
bit. Could you repeat that?
okay. If you say that there exists some a that has the property p, that's
Yes.
actually the same. Yeah, that's actually the same thing as saying that it's not the case that every a is not a p.
Yes.
And so you have this double negation thing going on, right?
Yes, but we are not doing that in here.
We kind of are actually, because this is a data constructor, right?
Yes.
So this takes PAA, right?
Yes.
Uh, so this is a basically a function that takes a PAA and returns a coend of P,
Yes.
essentially.
Yes.
So this is taking this PAA, right? If you go
Yes.
back to the intuition about arrows, this is a parameter, this is a hole, it's a negative position.
Yes. I understand so far. I don't know how we're gonna
Yeah,
get from that to the exists, but
yeah. So we have a negation here, right?
a negation here.
Because this is this is a parameter, right? This is a parameter. This is a hole. It's a
Wait,
negative.
now we are mixing okay, negative position literally is a negation now.
Well, yes, because it's a
Damn.
hole, right? It needs to be filled in. It's like there's not an A, but you can put an A there. You see?
Okay.
That's a yeah, that's a complete mixing, but whatever.
That's
The only the only problem with this analogy is that it's actually missing the second negation here, which is I'm kind of sad about.
okay. So, but okay. So I don't know, man. To me, this maybe I'm stupid. I don't know. I don't understand how we can convert an exists to a for all without doing some sort of negations in somewhere.
Well, we can just say Haskell syntax is weird and leave it at that.
Leave it at that. Okay, the logic behind this is that it should be possible to construct a coend using a value of any of family of types PAA, no matter what A we choose.
Yep.
But this is not what exists mean.
Actually, no, it is because this is an arrow, right? This is a P taking an A and going to an A. If you think
Yes,
about it that
but
way,
we are
that's the second
100% not
that's
saying.
the second negation.
We are 100% not saying no matter what way A we chose, it's fine. We are 100% not saying that it exists. Do you agree?
I agree.
So I don't follow, man. I don't follow. I'm trying my very best, but I don't understand.
Okay.
Just like an n can be defined using an equalizer, a coend can be described using a co-equalizer. All the co-edge wedge conditions can be summarized by taking one gigantic product of PAB for all possible functions BA. In Haskell, we do it like this. Uh,
Which is very unusual, but okay.
okay.
There are two ways of evaluating the sum type by lifting the function using the die map and applying it to the profunctor P, which are these ones. Again, lambda and rho, we've seen this before, right?
Yeah. Where diag sum is the sum of diagonal elements of P.
Yeah, just getting rid of this A so the signature here is nicer.
Okay.
Uh, the co-equalizer of these two functions is the coend, and it is obtained by identifying the values that are obtained by applying lambda or rho to the same argument. Here it is a pair consisting of a function from each way and an element of PAB, which is this, right?
Yes.
And the application of lambda and rho produces two potentially different values of this type, and in the coend, those two values are identified, making the condition automatically satisfied, the co-edge condition. And the process of identification of related elements is formally known as taking a quotient. Again, more mixed metaphors here.
Yeah, but this,
To
but
define,
yeah, but this one, I don't even see a glimpse of relation. But well, names.
yeah,
Oh
to
no, no,
define a
there is a no, there is a relation because we're gonna talk about rationals later. So that's the relation. Okay.
yeah, we are. To define a quotient, we need an equivalence relation tilde. Not sure why tilde, but well, okay. That is reflexive, symmetric, and transitive, just like equality. So these are the properties that it must have. This relation splits the set into equivalence classes, and each one has elements that are related to each other. And we form a quotient by picking one from each class. And the classic example is the definition of rational numbers as pair of whole numbers with, the usual
Mhm.
rule for equality of rational numbers.
Mm-hmm.
It's easy to check that it's an equivalence relation. A pair is interpreted as a fraction, where the numerator and denominator have a common divisor, are identified, and a rational number is an equivalence class of such fractions. Um, this is
Mm-hmm.
pretty standard if you know any number theory.
Mm-hmm.
You might recall from our earlier discussion of limits and co-limits that the home functor is continuous in the sense that it preserves limits, and dually, the contravariant home functor turns co-limits into limits.
Damn.
And these properties can be generalized to ends and coends, which are a generalization of limits and co-limits respectively, and we get this identity that converts one to
Okay,
the
so
other.
limits and colimits use a single vanilla covariant functor, and ends and coends they use very nightmarish profunctors.
Yeah, the second parameter makes it much harder.
I no, I disagree. Bifunctors are fine. I really think it's the contravariance thingy.
Okay.
Yeah, but here we
Uh,
go again with this. Yeah, still looking at this, I wanted to spend some time on the previous one to see if I can understand this, but I still can't understand it. How can we say that an exists becomes a for all without negations?
uh, well, if you interpret the arrow as an implies, I'm pretty sure there's a negation. Like if you look into like Boolean, freaking Boolean algebra.
No, there is a. I think it's the implication becomes not on the first or with the second. That's the equivalent with the implication truth table,
Right, it becomes a not with the first, right?
not with the first.
So there's a negation on the outside of this exists, right?
Yeah. Okay, that becomes a for all then.
Yeah, but then there's a not that goes in here because of Aristotle, essentially. But
Yes.
then, if you remember that we were using arrows as our intuition for the profunctor, there's a not here as well. So that's the second negation
So it
that
becomes
cancels.
positive on the other side. Is that what you're saying?
Yeah, basically.
Damn. Okay.
But there's still a tiny wrinkle in that there's not a negation here, so I don't know. It's a bit of a weird intuition, I guess.
Such weirdness, but okay. Uh,
It tells us that a function that takes an existential type. I think actually this one is a little better. A function that takes an existential type is equivalent to a polymorphic function, and this makes sense because that function needs to be prepared to handle any of the types that may be encoded in the existential type.
may be encoded in the existential type.
Yeah, because there may be like many different types that satisfy the exists, right?
Yes.
And this function that takes this needs to handle all of them.
Needs to handle all of them.
Yeah,
Ah, so that is why it becomes a for all.
yeah,
Oh, okay. Wait a moment. So the reason that an exists becomes a for all in Haskell is because of a language thing. Because in order to
basically.
treat all the possible cases, you need to be a for all.
Yeah,
Oh, okay, so we are okay. So there is a conflation going on here. There is a conflation between the semantics of the category theory thing and the semantics of the host language, which is Haskell in this case.
kinda. I'm pretty sure that if you go down, like, go into the whole formal theory, you could. I mean, there's a proof, right? So, I mean, I imagine there's a proof, but it may even be in this book actually later. But
Okay, anyway,
yeah,
it's the same principle that tells us that a function that accepts a sum type must be implemented as a case statement with a tuple of handlers, one for every type present in the sum. Here, the sum type is replaced by a coend, and the family of handlers becomes an end of a. Yeah, that is it. So there is a conflation going on. So that's why I didn't get it in the first try. That helped. Okay.
Yeah, like if you just look at this, it's kind of weird, but the paragraph helps a lot.
Yeah.
Yeah. And then the Ninja Yone dilemma, of course.
Ninjas.
The set of natural transformations that appears in the Yone dilemma may be encoded using an end, resulting in this formulation, which is okay. There's also a dual formula, and this identity is strongly reminiscent of the formula for the Dirac delta function, which is a function, or rather a distribution, that has an infinite peak at a equals z, which is, well, I'm not into calculus, so I actually don't know this function, but
Well,
whatever.
I was into calculus, but I think I saw this type of distribution like 2017. So I wouldn't call myself used to it.
Here, the home functor plays the role of the delta function, which is, I'm pretty sure if we were more into calculus, we would appreciate this more, but for me,
Yeah.
it's like, okay, this is interesting.
Together, these two identities are sometimes called the Ninja Yone dilemma. The fact that it has ninja on the name is kind of funny.
It really is. Like, I thought it would be like, oh, they sneaked a Yoneda lemma here, but no, actually, it's part of the name, which is like, okay. Um, to prove the second formula, we use the correspondence of the Yoneda embedding, which we saw a while back now,
Yeah. I have very little recollection of that as well.
and which states that two objects are isomorphic if and only if their home functors are isomorphic, or in other words, A is isomorphic to B if there's a natural transformation of this type, which
Let's try to read this thing. So what are the vertical bars again? I forgot.
uh, this represents
Is those
category.
are these brackets or vertical bars?
They're brackets.
Okay, brackets.
The Yeah, no, if I think I can zoom in.
Oh,
Yeah,
brackets.
see
Okay.
there. Yeah, there's a very tiny line here.
Okay, so how do you read
Uh,
this? I forgot.
right. If I'm not mistaken, this is like um, I think this is a category of this is a category of um, was it functors or natural transformations with the bars? Uh, I think it's functors actually. The category of functors from C to set, where
You have a home
the
set of
where the input is home set
that starts with A.
that starts with A, and the output is another home set that starts with B, and these are like type parameters.
Okay, I think you're right about the brackets. I think it's a functor. It's a functor that goes from C to set because we are basically creating another home set, and the home
Yeah.
set starts with morphisms coming from the origin category, which is C, and starting with elements A, and going to another home set members in which the first member is B. So it's okay. I think this would be better with a drawing. I don't know why we don't have a drawing in this case, but
Yeah. It expects you to remember things basically.
okay.
Yeah, so basically A is isomorphic to B if there is a natural transformation of this type, which is an isomorphism, which means there needs to be an inverse.
Yes.
Uh, Let me try to, there we go, make this a bit smaller. We start by inserting the left-hand side of the identity inside of a home functor that's going to some arbitrary C. So the left-hand side of the identity is this one. So we put this in a home functor that goes to C.
Mm-hmm.
Using the continuity argument, we can replace the co-end with the end. So this,
Which is that equality up there that we saw.
Yeah, this exists becomes a for all outside of the.
Ah, okay, so maybe that's another reason they use the integral because in integrals you can actually put stuff from outside inside. Okay, I see.
Okay, so they use the symbol for algebraic reasons, I suppose.
Yeah. Okay, so set is an operation that you can put inside the integral. Okay. But you need to change the subscript. Okay. Interesting.
Yeah, it's literally this, right?
No,
The
no, it's
function
literally
that.
that. But now I kind of understand. Well, I'm not gonna say I understand because I don't have an intuition of coends and ends yet. But I will say it makes a tiny bit more sense why they chose that symbol, as you said, because
Okay.
of algebraic reasons.
Okay, so continuity arguments, we use the identity, so this exists becomes a for all on the outside, right?
And you pass the set to the inner thing.
Uh, no, the set takes the like this becomes a for all and then a polymorphic function. So this is
No, 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 no. The set was on the outside. We pass it to the inside.
yeah. This is inside of the for all now. Before
Yes,
there was an exist inside of it.
yes. We cannot take advantage of the adjunction between the product and exponential, which is kind of nuts.
Right, this product and this exponential. We saw something similar before.
Wait a moment though. Go up. So I want to understand. We are kind of using that trick of understanding functions as an exponential, right?
Yeah.
I think we are using that. So why are we grabbing the fz from the left guy?
This is a product, right?
Yes,
This means that the set product comma c is a curried function, is an uncurried function,
yes.
and we're currying it.
Ah. So the exponent are the arguments, right?
Yeah.
Okay, I see. I see. Kind of crazy, but okay.
And then we perform the integration in quotation marks by using the
Using the
Yoneda
Onedo
lemma
lemma.
to get this, where okay, we have c taking an f of z, and this is the output, and the input is a c from z to a. So
We are going from a home set to
a
to
function
a
basically.
function. Okay, I need more intuition to understand this, but the z
Okay.
disappeared. So I think that's what he meant by the limit thing. The z completely disappeared. I see.
Yeah, this is basically saying for all z, um, it takes a function from z to a and takes an f of z and returns a c or something.
Yeah, that's kind of crazy, but let's continue. Notice that we have
So we
used a
use
contravariant version of the Needle lemma since the functor CFZ is contravariant in Z. This exponential object is isomorphic to this home set. Let's try to use this version. Let's like imagine that the middle version doesn't exist. So we are going from set CZA CFZ to set of FAC. Hmm. So the CZA became the F of A, and the CFZ became only C.
well, the c is the output of this function type, right?
Yeah.
So it's in the output side of this home set.
No, the C would be on the output side. I'm trying to understand what happened with the home set and the FZ.
The home set and the fz. Well, this is a functor in C from Z to A. Well, this is a home set in the category C from Z to A, right?
Yes, this is a home set.
Uh,
Interesting.
yeah, this is a home set. Oh, this is a home. This is a home set in category set where on the left we have a home set in category C from Z to A.
Yeah.
So this is basically an arrow ZA in category C, right?
Yeah, but we have a for all going on. So are all it's basically everyone pointing to A.
No, no, no. But the variable introduced in the for all is actually Z.
Exactly. So Z is the for all Z's, then this. So we have everyone pointing to A on the home set.
Yeah, we do.
I need more intuition about this to make a judgment, but let's just continue. So finally, we take advantage of the another embedding to arrive at this isomorphism. Okay,
Which is what we were trying to get to begin with, right?
yes. Uh,
So QED, and then profunctor composition. Again, if you think about profunctors as arrows, this actually makes a lot more sense.
I would say so.
Uh, yeah, let's explore further the idea that a profunctor describes a relation, or more precisely, a proof-relevant relation, meaning that the set PAB is represents the set of proofs that A is related to B. So if we have two relations P and Q, we can try to compose them. We say that A is related to B through the composition of Q after P if there exists an intermediary object C such that both QBC and PCA are non-empty,
Mm-hmm.
which is a very dense sentence, but it
Yeah.
actually makes sense if you look at it.
The proofs of this relation are all pairs of proofs of individual relations. Therefore, with the understanding that the existential quantifier corresponds to a coend and the Cartesian product of two sets corresponds to a pair of proofs, we can define composition of profunctors using the following.
And
So
I
the
think actually the Haskell notation makes it easier to understand.
let's go with that then. So you have a procompose.
That's a very weird name, by the way.
Procompose. Which grabs two things, two profunctors, a Q and a P, and
Arguments A and B.
arguments A and B, and we are using JDTs here. So we receive the Q, we receive the P, and we actually compose them. That's kind of funny. The composition doesn't disappear; it actually preserves both of them. Oh,
Yeah,
my bad. The C disappears. Okay,
the C disappears, yeah.
okay, okay,
So
okay, okay.
basically, if we have a Q from A to C and a P from C to B, we can glue them together.
Yeah, that makes sense. If they are, if all of the functors with contravariance, they are about functions.
Yeah, this is using generalized algebraic data type or GADT syntax, which is
Because the C
in
is free.
which, yeah, in which a free type variable, here C, is automatically existentially quantified.
Yes.
So if you uncurry this is equivalent to this.
Yes, actually. Uh, okay.
The, un the unit of this composition defined like this is the home functor. And this immediately follows from the Ninja-Yone lemma, which we just saw. It makes
It,
sense, therefore, that to ask the question if there is a category in which profunctors serve as morphisms.
of course
Because
there
of
is.
course, of course there is. With
Uh,
the caveat that both associativity and identity laws hold only up to natural isomorphism.
Damn.
Which is probably why this procompose thingy remembers both Q and P, I guess.
What is a natural isomorphism again?
It's a natural transformation which is isomorphic in the sense that you can invert it and get back to
But
the
you
original
can't
thing.
do that. That's why we made adjunctions.
No, 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 no. It's a natural transformation that has an inverse. And
Yes, but that's the problem. Do you remember in the chapter about adjunctions that part of the reasoning that we went that route was because defining an invert of a functor is kind of
but this is not an inverse of a functor, it's an inverse of a natural transformation, which is slightly different.
okay. You're right, but that sounds worse.
But we've been seeing natural isomorphisms for a while now.
I don't recall. Do you have any examples? You don't have to scroll up to the example. You can just say if you remember as well.
Yeah, there's one in this same chapter, just when we are talking about ends and coends at the very beginning, actually.
You're saying that that is a natural.
Yeah, it says it says that uh, there must be a natural isomorphism between, I don't remember what actually. My brain's kind of fried today.
Okay, anyway, let's finish. We are on the last page.
Such a category where laws are valid only up to isomorphism is called a bicategory, which is more general than a two category. Um,
That's funny.
so we have a bicategory prof. So every professor you've ever had is a bicategory, in which the objects are categories, morphisms are profunctors, and morphisms between morphisms, aka two cells, are natural transformations. Um, in fact, one can go even further because besides profunctors, we also have regular functors as morphisms between categories. A category which has two
Damn.
types of morphisms is called a double category.
Okay, so you have the two category, the bi category, and the double.
Yeah. And profunctors play an important role in the Haskell lens library and in the arrow.
Okay.
And that's the end of the chapter.
Okay,
That
let's
was
just. Okay, go on.
that was very dense.
Yeah, let's go all the way up to the beginning of the chapter so you can show me the natural isomorphism and then we can finish.
All right.
Where is the natural
Relationship,
isomorphism?
relation between objects, following signature, profunctor, proof relevant relation, um, profunctor, translations to the old keys, blah blah blah. Uh, I think it's around here. Naturality condition, and then coends, unlike cones, wedge condition, universal wedge, projection, discrete category, parametricity, polymorphic projection, uh, dinaturality, equalizers, uh, lambda and row, natural transformations as ends. I think it's here actually.
Okay, according to Wikipedia, if for every object X in a category C, the morphism, whatever, is an isomorphism in D, then okay, so I think I got it. So it is related to the natural transformation, but so basically the rationale is if you have a morphism in one category, and after you do the natural transformation, that morphism becomes an isomorphism on the other category, in the result category, that's a natural isomorphism.
Uh,
So when you translate when you lift the morphisms, I think that's when
yeah,
that happens.
yeah. Actually, they are mentioned way back in chapter 12. Like, where is it?
There's a lot of text here. I don't know if you're gonna be able to find it.
Yeah, limit is a natural isomorphism. Chapter 12 is like the first notable mention of this particular term.
Yeah, but that's a lot of text though.
It is a lot of text, yes.
I'm gonna finish the recording now, okay?
Bye, future people.
Bye.